Imagine a world where an AI agent, whether a virtual NPC in a game, a robotic assistant, or a digital performer, can react in real time to evolving natural language commands. Walk forward, then squat, then stand up, and not just mechanically, but with smooth, lifelike motion, seamlessly transitioning between actions without stuttering, lag, or unnatural breaks. This isn't science fiction. It's the future of streaming human motion generation, and today we're diving deep into FloodDiffusion, a groundbreaking framework that redefines how we generate continuous, text-driven motion in real time, with state-of-the-art quality and minimal latency. The problem: why streaming motion is harder than it seems. Most existing methods for generating 3D human motion from text are designed for a batch setting. You give a full sentence, a person walks across the room and then turns around, and the model outputs the entire motion sequence at once. But in real applications, like interactive games, robotics, or virtual avatars, the text prompt isn't static. It changes on the fly. The agent must react instantly, not wait for the full sentence. And yet most models can't handle this. One common workaround is chunk-by-chunk diffusion. Generate a few seconds of motion, then refresh with the next prompt. But this leads to high latency. You have to wait for a full chunk to be generated before outputting anything, and unnatural transitions between chunks. Another approach uses autoregressive models with a diffusion head, like MotionStreamer. These generate motion one frame at a time, which reduces latency. But they struggle to leverage long-term motion history effectively, and their performance degrades when the text changes mid-sequence. So what's the missing piece? Enter diffusion forcing, but not the way you think. Diffusion forcing was originally developed for video generation. The idea is elegant. Instead of applying the same noise level to every frame, you assign different time steps to each frame. This allows the model to denoise frames at different rates, enabling streaming generation with low latency and direct access to past frames. In theory, this should be perfect for streaming motion. But here's the catch. A vanilla implementation of diffusion forcing fails miserably on human motion. Why? Because motion is fundamentally different from video. It's a 1D time series, not 2D spatial video. Text prompts can change at any moment, and the model must reflect those changes immediately, not just at fixed intervals. So we asked, what if we tailor diffusion forcing specifically for motion? And that's how FloodDiffusion was born. The key innovations: 3 critical modifications. We didn't just apply diffusion forcing, we redesigned it for motion. Here are the 3 core changes that make it work. 1. Bidirectional attention, not causal. In standard diffusion models, attention is causal. Each frame only sees past frames. But in our streaming setup, the active window, the portion of motion being denoised, includes frames at different noise levels. Some are nearly clean, others still noisy. If we use causal attention, the model can't see the latest text prompt when denoising a frame that's already partially reconstructed. It's like trying to read a book where you can only look back at the previous page. So we replaced causal attention with bidirectional attention within the active window. This ensures that every frame can attend to the most recent text, even if it's not yet fully denoised. The result: better alignment, smoother transitions, and more coherent motion. 2. A lower triangular time scheduler, not random. In vanilla diffusion forcing, time steps are sampled randomly for each frame. This creates unpredictable noise levels. Some frames are almost clean, others are still full of noise. But randomness breaks the temporal structure of motion. The model can't learn consistent dynamics when the noise schedule is unpredictable. Instead, we introduced a lower triangular time scheduler, a deterministic, cascading schedule where frames progress from noise to data at a fixed rate. Imagine a wave of denoising moving forward through time. Each frame is denoised only after the previous one is ready. This creates a clean, predictable flow, and crucially, it enables streaming locality. That means, at any moment, the model only needs to process the current active window. No full sequence is required. This gives us 1 frame latency and bounded response time, no waiting for a chunk. 3. Continuous frame-wise text conditioning, no refresh logic. Most streaming models rely on prompt refresh detection. They must detect when the text changes and trigger a new generation. But that's fragile. What if the prompt changes subtly? Or mid-sentence? FloodDiffusion eliminates this need entirely. Instead of treating text as discrete events, we model it as a continuous, time-varying signal. Each frame is conditioned on the current text prompt, not a cached version. We use a T5 encoder to extract text features, apply rotary embeddings to align them with motion tokens, and inject them via a biased attention mask. This ensures that as soon as a new prompt arrives, the model immediately reflects it in the next frames. No detection, no refresh, no delay. The result: state-of-the-art performance without compromise. We tested FloodDiffusion on 2 major benchmarks, HumanML3D and BABEL. On HumanML3D, we achieved an FID of 0.057, outperforming all prior streaming methods and matching the best non-streaming models. On BABEL, which evaluates time-varying prompts, for example, walk, right arrow, turn, right arrow, jump, FloodDiffusion dominated all baselines in R precision, multimodal distance, and streaming-specific metrics like peak jerk and area under jerk. And in a user study with 100 participants, FloodDiffusion outperformed both PRIMAL and MotionStreamer across preference, transition, and consistency, and came within a hair's breadth of real human motion. Why this matters: a new paradigm for real-time AI agents. FloodDiffusion isn't just a technical improvement. It's a shift in philosophy. It's trained end-to-end on time-varying prompts, no need for inference-time tricks. It generates smooth, continuous motion with real-time latency. It does not require prompt refresh detection, stopping, or manual optimization. It preserves the exact data distribution. No ELBO approximation, no proxy loss. And crucially, it's built on latent diffusion, so it's fast and efficient. We use a causal VAE to compress motion into a low-dimensional latent space, then run diffusion only in that space, keeping streaming latency low. The bigger picture: what's next? FloodDiffusion opens the door to more intelligent, responsive AI agents. Imagine a robot that understands natural language commands in real time, pick up the cup, then walk to the table and sit down. Or a virtual assistant that can react to changing environments. Stop. There's a dog on the sidewalk. Future work. Integrating audio, force feedback, or environmental context. Using LLMs to interpret complex commands like repeat what you did last time. Or training on long-term motion data to improve consistency. But the foundation is already here. A diffusion forcing framework that's not just adapted, but reinvented for motion. Final thoughts. FloodDiffusion proves that diffusion forcing isn't just a video trick. It's a powerful, flexible framework for any time series generation task. With the right architectural and scheduling modifications, it can achieve SOTA performance in streaming motion generation, with real-time responsiveness and unmatched coherence. And it's not just theoretical. The code, models, and weights are open-sourced. So if you're building the next generation of interactive agents, this is your starting point. Thanks for watching. If you found this deep dive valuable, subscribe and hit the bell, because the future of AI motion is streaming, and it's just getting started.